Okay, so enough with the derivation of the Laplace transform table. Now we know how we kind of came up with all five of these equations or relations here for the Laplace and inverse Laplace transform. Now let's actually use the Laplace transform as an operator. And when we do that, we can do some pretty cool things solving differential equations. Okay, that's what ODE stands for in the title here, solving ordinary differential equations. PDEs are partial differential equations, they're a bit different, but ODEs, let's just focus on those right now. And let's just do kind of the most classic case, let's say the derivative. So one notation for the derivative is d by dx. Another one is if the function's f, it could be f prime. Another one could be, the one that we'll be using actually is going to be a capital D with a lowercase x there. Okay, there's all sorts of notations that you can use, but we're going to be using this one. Okay, so let's say the first derivative with respect to the function x, so we can call it x of t. Right, if we have some function x of t, the derivative is going to be equal to t. So if we have some function x of t and we take the derivative of x of t, we're just going to get t back. And anytime we're solving a differential equation with a first order derivative, we need an initial condition. So an initial condition is just what the function equals when x is 0. When t is 0. So x of 0 when t is 0, that's going to be, let's say it's 2. Okay, so if we were going to plot this function x of t, right, we know the y-intercept would be 2 here. If they're not the y-intercepts, right, I guess it would be the x-intercept, and this would be t. We don't know how the function's exactly going to look. It could look like this, right? But all we know is that as we kind of traverse in either the left or the right direction in the t direction, the derivative of the function, so the instantaneous slope, is going to increase linearly. So it's going to kind of go like this. My guess is it'll look something like a parabola, but we'll figure it out right here. So an important thing you need to remember with the Laplace transform, I'm not going to, some things are worth deriving, but this honestly isn't. So if you take the Laplace transform of a derivative in first order, okay, that's going to be equal to s times the Laplace transform of the original function. So if this is the derivative of x of t, that's going to be equal to s times the Laplace transform of x of t minus the initial condition x of 0. So that's why we need this part right here, because it's kind of part of our formula. And I'm going to bring all this up. So I'm just going to paste it maybe right here, make it a bit smaller. It's going to be part of our table here. Okay, and that's all we need to know for this question. We can also kind of apply this formula to higher order derivatives. So for example, if we took the Laplace transform of the second derivative, so the notation for that is d squared, with a little x here, so the function x. Second derivative, that's going to be equal to s squared times L of x of t. So the only difference now is that this s, there's another s joining it, multiplying, and it's going to kind of follow a pattern. So we're going to do that, and then we're going to minus s of x, or I don't even need a bracket there, I'll go s times x of 0. So what we have so far is the variable s squared times the Laplace transform of x of t minus s times the initial condition. And then since it's a second order derivative, we always need two initial conditions. So it's going to be this first initial condition, and then minus the derivative of x at the initial condition. So with this second order derivative, we need two conditions. We need the initial condition, and we need the initial condition with a derivative. Okay, there's kind of a pattern here. Like if we're doing a third derivative, I'll have to write a bit smaller. So the third derivative of the function x of t, bit of a pattern here. It's going to be s cubed now times the Laplace transform of x of t. Okay, minus, you can kind of guess, s squared times x of 0. So that's our first initial condition. Minus, bit of a pattern. So the order of the s kind of descends as we move to the right. Minus s times x prime of 0, and then you guessed it, we're going to subtract x double prime of 0. So I'm going to add these two to the kind of table up there as well. Okay, I'm going to paste it right about there for reference in these questions. It's going to be pretty useful, right? Okay, so now that we kind of covered that, let's get right into this question here. So like I was saying before, we can apply the Laplace transform into an equation as an operator. So anytime we see a plus or a minus sign separating two terms, we can apply the Laplace transform to both of them. In this case, we don't have that. We just have the derivative of our function is just going to be equal to t. And we know just from integrating both sides, right, if this was, or actually if we had dy by dx equals x, right, we'd multiply both sides by dx, so we'd get dy equals x dx. We'd integrate both sides, so we would just get y equals 1/2 x squared plus c. We need to know the initial condition for c. We just put 2, blah, blah, blah. So we know the answer here is 1/2 x squared plus 2, or 1/2 t squared plus 2, because our variable's t. But let's practice using the Laplace transform, and we should get the same thing. So if we apply the Laplace transform to both sides here, because it is an equation, so this should work, the Laplace transform of what the derivative of the function is should equal the Laplace transform of just the variable t. Now, we know that the Laplace transform of a derivative right up here is going to be s times the Laplace transform of x of t minus x of 0. So it's going to be s Laplace transform x of t minus x of 0, that initial condition they gave us, right? And that's going to be equal to, well, the Laplace transform of t, we're going to have to use the table on the left here, t to the n, where n is just 1, so it'll be 1 over s squared. 1 over s squared. And just kind of filling in what we know here, instead of x of t, I'm just going to put s. So s times the Laplace transform of x, and then remember our initial condition is positive 2, so we're going to minus 2, right, minus x of 0. It's going to equal 1 over s squared. So now that we have applied the Laplace transform, we're going to try and solve for this L of x, because once we do that, we can take the inverse Laplace transform of the other side, and then we can figure out what x is. Okay, so the first thing I would do is probably add 2 on both sides, and once we do that, we're going to divide by 2. So we'll get the Laplace transform of x is equal to 1. If we divide both by s, we'll get 1 over s cubed plus 2 over s. Okay, so now if we just want x, right, we have to take the inverse Laplace of x. So we get x equals the inverse Laplace, right, of 1 over s cubed. And then since it's linear, I'm going to take the Laplace separately. So I'll go plus the inverse Laplace of 2 over s. Okay, and just using our table here, if the inverse Laplace of 1 over s cubed, that means that n is 3, so this will be t to the 3 minus 1, so t squared, over 3 minus 1 factorial, so over 2. So this would be t squared over 2. We can kind of see where this is going. And then plus, we got inverse Laplace of 2 over s. So the inverse Laplace of 1 over s is 1. So multiplying that by 2, we just get 2. So we get plus 2. And this is exactly what we get when we integrate it using our integrals for differentiation. Just this time using the Laplace transform. So notice how we didn't have to apply the initial condition at the end. We kind of integrated it within this formula here, solving for our function x of t, which is pretty cool because if we had to integrate it, we would do what we did before, like I showed you with the integrals, and then we would have to figure out what plus c would be using that initial condition. But this way it's just a bit faster at the end, and you'll find that it's better if you have functions where you can separate two things with a plus or minus sign, because then you can take the inverse Laplace of both of those. It'll be a lot easier, and you'll see what I mean in the next couple problems here. So let's, now that we did that, let's do a bit of a harder one. Let's go, actually let's say, I'll go d squared x minus x. So x is just the function x of t equals 0. So if we have some function, we're taking the second derivative of that function, and we subtract that, and we subtract the function itself, x, from its second derivative, then we should get 0. So I'm going to guess that it's going to be some sort of exponential function. And one thing you could say is, oh, well, that just means x equals e to the t, because the second derivative of e to the t is e to the t, and then minus e to the t is just 0. Well, you're right, except we're going to need to put some initial conditions on this, right? So in the question I made, I said that x of 0 equals 3, and since it's a second order derivative in the equation, we need x prime of 0 as well. So I'll go x prime of 0 equals, I don't know, let's go 1. Well, now this won't work, right? Because if we put 0 in for t, we're going to get e to the 0, which is 1, and 1 does not equal 3. So we're going to get some other function. It's probably going to be an exponential, just kind of looking at this equation. But we're not quite sure what that's going to be to meet both of these criterion for the initial conditions. Okay, well, we know that we could take the Laplace transform of everything with a plus or minus sign between it. So let's take the inverse, the regular Laplace of d squared x, and let's subtract the Laplace of just x, and we know that's going to equal 0, or the Laplace of 0, but we know that the Laplace of 0 is just 0. Okay, so now we have to kind of consider what both of these are going to be. So the Laplace transform of d squared x, I wrote up here, it's going to be s squared L of xt, so s squared L of x. And then we're going to get minus s times x of 0. And then we also get minus x prime of 0. So we took care of this part right here. Then we're going to go minus whatever the Laplace of x is. Actually, we don't need to do that. That's not even a derivative. So we can just go minus L of x. I could have written it a bit bigger. Equals 0. Okay, well, we know x of 0 and x prime of 0, so let's just plug that in. X of 0 is going to be 3. So we can go minus 3s, and then we can go minus 1, because x prime of 0 is 1. So s squared L of x minus 3s minus 1 equals 0. So now we're entering the s domain, right? We have an s squared, we have a 3s, and once we take the Laplace transform of x, we would also get things in terms of s. So what we want to do now is we want to solve for L of x, right? Because right now we have s squared times L of s, or L of x, and it's kind of buried within all this other stuff. So let's add, let's just think here. Just thinking that we could do this. Oh, it's because I forgot this here. Because we also have this minus L of x, okay. Okay, equals 0. So now what we want to do is, we have two things with L of x in them. We want to move everything that doesn't have an L of x to the other side. So we'll get 3s plus 1 on the other side once we move this over, because they don't have an L of x. And now we just have s squared L of x minus L of x. So we can factor out that Laplace transform of x. And that's going to be multiplying into s squared minus 1. Okay, and if we just want L of s, or L of x, we just divide by s squared minus 1. So the Laplace transform of x equals 3s plus 1 over s squared minus 1. Okay, so now what we can do is, first of all, let's factor this. So we can go s plus 1, s minus 1, because it's a difference of squares, which is always nice to see. And there isn't really like a thing in our table for something like this to take the inverse Laplace transform. Usually, if we just have L of x equals a function in terms of s, we would take the inverse Laplace of that. But for the 5 things in our table, we don't have that. And if that ever happens, and it's some weird fraction, typically you're going to want to split it up into multiple fractions that are adding and subtracting, because we know that Laplace transforms are linear, so we can just split them up into multiple smaller fractions and take the Laplace transforms of those. So partial fraction decomposition is probably going to be the way to go on this one. It's going to be the way to go in a lot of these, I'm going to be honest, so you might want to practice your skills there with decomposing fractions. I know it can be kind of annoying, but it's necessary in these ones. So we want something that's going to give us some constant over s plus 1 plus another constant, I'll call it b, over s minus 1. Now how can we do that? Well, remember, we can just cross multiply. So if we multiply both sides by s plus 1, s minus 1, on the left we just get 3s plus 1 because that will cancel. And on the right, we're going to get the s plus 1s here canceling, so we'll get a times s minus 1, and we'll get plus b times s plus 1. Okay. So now we don't have any more fractions, we just have kind of an equation here with 3 variables. And when we have 3 variables, we want to figure out some way to get rid of 2 of them. So one way we can do that is say that s is equal to 1. Okay, so we can say, I'll write let s equal 1. That way, actually I'll move it over a bit. So if we say let s equals 1, that way we get 3 times 1 plus 1 equals a times 1 minus 1 is just a times 0, which is 0. So we'll just get b times 1 plus 1. 3 times 1 is 3, plus 1 is 4, so 4 equals 2b. Right, and then we divide both sides by 2, so we get b equals 2. Okay, now that we have b, let's try and figure out a way to get a. So I'll copy this down here. So using the same kind of equation here, let's figure out a way to get a, right? Because we got rid of a in the first one, saying s was 1, so let's say let s equal negative 1 now, because then if s is negative 1, this b term will go away. So we'll get 3 times negative 1 plus 1 equals b times negative, the b's gone. So it'll be a times negative 1 minus 1. So 3 times negative 1, well, that's going to be negative 3, plus 1 is negative 2, and this will be negative 2a. So that means a equals 1. Right, but what does this even mean? Well, let's go back to our original equation here. I'm going to copy and paste this. Because we're copying this, I'm just going to kind of plop it down here. So what we said was we started with this kind of big ugly fraction, and by factoring the bottom, splitting it into linear factors, we can split it up into a constant a over s plus 1 plus a constant b over s minus 1. We just solved for those constants. So b was 2 and a was 1. So this is going to be equal to 1 over s plus 1 plus 2 over s minus 1. So if we were to kind of simplify this into one fraction, we would just get this original one back. But we don't want to do that because seeing these pluses and simpler fractions are our best friend when we're solving Laplace transforms. So since we know that that's what L of x is equal to, I'll write L of x here. So the Laplace transform is 1 over s plus 1 plus 2 over s minus 1. We can just take the inverse Laplace of both sides to get x. So x is the inverse Laplace of 1 over s plus 1 plus the inverse Laplace of 2 over s minus 1. Right, and just kind of looking at our table here, 1 over s plus 1, inverse Laplace, 1 over s plus 1, that'll be this guy right here. So that means lambda is -1, so this will be e to the negative 1t. So this will be e to the negative t, let me just write it here, equals e to the negative t, and then we have inverse Laplace of 2 over s minus 1, which is really 2 times 1 over s minus 1. So 1 over s minus 1, alpha, or sorry, not alpha, lambda is 1. So this will be 2e to the 1t, or just 2e to the t. So plus 2e to the t. So we've solved the equation. This is what x of t is equal to. And if you don't believe me, we can always check our answer by kind of looking at the original thing and plugging in our initial condition. So first, let's make sure the second order derivative minus x is just equal to 0. So I'll write d squared x minus x equals 0. Okay, so remember, this is our x. It's not just one of these, it's the whole thing. So the second derivative of that, well, the first derivative is, it's going to be negative e to the negative t plus, I guess, just 2e to the t. Right, and if we take that again, we're going to get positive e to the t. Let's see here. So second order derivative of x, negative e to the negative t, plus 2e to the negative t. Oh, right, okay. So this is going to be positive, so I'm just thinking it through here, plus 2e to the t. So this is your first order, this is your second order derivative. So this bottom one here is d squared x, so we're going to write e to the t plus 2e to the, e to the negative t plus 2e to the t, and then we're going to go minus our function itself, x, which is the same thing, right? It's e, so it's minus e to the negative t plus 2e to the t. So if this was a first order derivative, this wouldn't work because we'd still have a negative on this e to the negative t. The 2e to the t kind of remains unchanged, but this part here, it's basically saying like the second derivative is equal to the function itself, which is true because this is equal to this. So when you subtract them, you just get 0, so that checks off. And let's just check our initial conditions. So we said that the first order derivative evaluated at 0 was 1, and x of 0 was 3. So let's just plug in 0 for t. So e to the negative 0 plus 2e to the 0. Right, this is going to be e to the negative 0, which is 1, plus 2 times 1, which is 3, so that checks out. And let's just evaluate the first derivative at 0, and we should get 1. So remember, the first derivative was negative e to the negative t, and we're evaluating at 0. So it's negative e to the negative 0 plus 2e to the 0. This is negative 1 plus 2, which is just positive 1. So that also checks out. So that's how you can kind of verify your solution. Should I do one more here? Yeah, I'll actually do 2 more. I'll make this a pretty long video. So let's go, actually no, maybe I'll just go 1 more. I'll go d squared. I have a couple harder ones that I'll do in a separate video. So d squared x minus d cubed x equals 0. And I'm going to say, remember we need 3 initial conditions for this because we have a cube there. So x of 0 equals, I'm going to say x at 0 equals x prime at 0, which equals x double prime at 0. I'm going to say that they're all equal to 2. So if you evaluate all of them at 0, you're going to get 2. So we're going to go the inverse Laplace of d squared x minus, or sorry, not the inverse, the normal Laplace, and then the Laplace of d cubed x, that's going to equal the Laplace of 0, which is just 0. So it's going to be like this long thing here. Just using our rules of derivatives and Laplaces, we're going to get s squared L of x minus sx of 0 minus x prime of 0. And then we're going to get minus in brackets because we want to distribute that, right? Can't forget that. It's an important step. Of x minus s squared x of 0. That's an initial condition coming there. Sx prime of 0 minus x double prime at 0. We're going to fit in that equals 0 there. Okay, so let's kind of distribute this. Once we distribute, we can actually factor out an L of x and cancel out a bunch of stuff. So instead of like distributing it, and like I'm honestly not going to have enough room, so I'm going to write, after you distribute and factor, you'll get L of x times, let's see, s squared minus s cubed. After you cross a bunch of stuff out, you're going to get actually plus 2 s squared plus 2s squared is going to be equal to 0. Move that to the other side. You're going to get L of x. Right, we move this to s squared over, and we just divide by this, right? S squared minus s to the 3. Okay, cool. Now we can kind of cancel a bunch of stuff. So we see an s squared on the top and both terms on the bottom, so we can kind of cross that out there. So it'll be 2 over, and we just have to assume s doesn't equal 0. So 2 over 1 minus s. And it's going to be negative 2, of course. I don't know why I wrote positive. So if we want to, like right now we have 1 over s. If we're taking the inverse Laplace transform of this, we want this to be s minus 1. And if we want that, we just have to flip both sides. We have to make this negative, this positive. And in order to do that, we have to take the negative of this whole thing. So this negative 2 will become a positive 2, and it'll be 2 over s minus 1. Okay, and that means that x is going to be the inverse Laplace transform of 2 over s minus 1. And just using our table there, we'll get 2e to the t. Okay, and that makes a bit of intuitive sense, right? We probably could have solved this even in our heads, because the second derivative of this is just 2e to the t. The third derivative is just 2e to the t. And we know that all of these initial conditions are equal to 2, so we just tack on a 2 in front. Like if the initial conditions were equal to 3, we put a 3 here. If they're 5, we put a 5 here. If they were negative, it would probably matter a bit more. But if all of them are positive, like taking the derivative of this, it doesn't change it. And it's always going to be equal if it's like the first, second, third, fourth derivative. So these questions can honestly be done in your head, but that's how you do them with the Laplace transform. And it's always like it's not convenient, but it's a consistent, reliable way of solving differential equations. So I'm going to go over a few more difficult problems in my next videos, but that's kind of the basic idea. I know we did a few harder ones for sure, but just building off of these two tables here, actually introducing the Laplace transform as an operator, right? Knowing it's linear, looking for plus or minus signs can really be helpful. So thanks for listening. I'll see you in my next one.